Hi guys, welcome to this fifth tutorial looking at the analysis of athlete monitoring data using linear mixed models. Today we are going to look at the interpretation of the models that we've produced. So for this tutorial you will require the interpretation workbook to be open. You can also open the script in SAS if you want to follow along and rerun the analysis to see where we get the outputs from. But everything is actually in the interpretation workbook, so you don't necessarily need to. So we'll jump straight in. We're going to start with the group Z-score categorical random intercepts model. If you do want to run the output again, it is the output. It's a prop mix that starts at line 17. So it runs from line 17 to line 39. And as you can see, I've picked out the most important parts as I see them in terms of understanding what's going on with the model and what we can glean from it. So we've got the covariance parameters, which give us the between participant variance and the within participant variance. We've got the least square means for each Z-score group. We've got the differences between these least square means. And then I've copied the estimates for athlete 9 only. You could play around with any of the other athletes if you wanted to. So first of all, like last time, we have created the between subject standard deviation or the pooled standard deviation by square rooting the sum of these two estimates. And I've also just square rooted the estimate lower and upper bounds for each row to give us a between athletes standard deviation and a within athletes standard deviation. So those two parts are broken down and this part is pulled together. We have the least square means for each group. So when low sleep is experienced, we expect 49.1 to be the well-being score the following day. It's 56.73 for high sleep for medium sleep, and 63.81 for high sleep. And then what I've done here is I've just subtracted the upper from the estimate. And because these confidence intervals are normally distributed, that gives us a confidence limit difference, which we can use when describing the results. For the covariance parameters, you'll see that's not normally distributed because it follows a chi-squared distribution, so you need to square root both individually. I've then calculated the standard deviation below the mean using the between athlete standard deviation estimate and one standard deviation above. So again, that's just adding from the estimate. And the reason I've done that will become clear soon. We then have the differences of the least square mean, so just the comparisons between the two, and you can see that in all situations, the right-hand group is greater than the left-hand group because of this negative estimate. So medium sleep would expect a higher well-being score than low sleep. Likewise, high sleep would expect a higher well-being score than low sleep. I've then created effect sizes using our pooled standard deviation. So this is just the estimate divided by the pooled standard deviation to give us the effect size. And I've done the same for the lower and the upper confidence intervals. And because we're working with negative numbers, the higher number or the higher low number, so minus 0.6 is a lower rather than the upper because it's further away from 0. Finally, we've got the estimates, and these are the estimates for athlete 9, as I said. We have the estimate for the intercept, and then the estimate for the 3 individual sleep amounts. And then this value is the estimate subtract the within participant standard deviation. And then we have the same estimate add the within participant standard deviation. So those are the results that we've got. What information can we take from them? So first off, the easiest thing to do is to look at the differences between the z-score groups individually. So taking the p-value that's in column H, we can see whether the difference was significant. And then using the effect sizes, we can quantify the difference between the groups. So one thing we could say now is there's a small significant difference between daily well-being at medium sleep and low sleep. And we could use the p-value and the effect size to quantify that difference. And then to show that difference in real terms, we could add in the estimates that we've taken above. So for medium sleep, 56.73 plus 4.11, so 56.73 here and 4.11 there. And then for low sleep, we could use the same estimate, the same column for their estimate, and then the confidence limit difference, which is there. And it just gives a full picture of what's going on. Similarly, we could do the same for low sleep. So again, low sleep is a significant difference, and then the effect sizes are here. This time I haven't used the least square means, but you can if you want to. So low sleep results in a significantly lower daily well-being score the following day than high sleep. That was a large difference. And then again, just on a similar thing for the difference between medium sleep and high sleep. So there are three pairwise comparisons, but now we need to look at what information we can actually gain from that. So I guess the summary is that there's a general trend of daily well-being increasing as sleep increases, and that's shown by the least square means estimates, which rise from 49 to 63. And so, unsurprisingly, the interpretation of that is that you can expect a higher daily well-being score after high sleep than after low sleep, or after medium sleep. But if we also look at the differences between low and medium sleep and medium and high sleep, we can see that the effect sizes are very similar, minus 0.51 and minus 0.47. So it seems like it's basically a linear trend where the more sleep you get, the better you feel the next day. And it's not just a case of low sleep being really bad for you or high sleep being really good for you. And that gives us a nice rationale for going on to the using the covariates that we've used in the next model. So then we can look at the within and between participant standard deviations. That should be participant. And we can see that these are almost equivalent. So basically 10.78 is almost exactly the same as 10.59. The only difference is there's a bit more uncertainty in the between athlete standard deviations. So we can use these now to talk about a typical athlete response. A typical athlete response can be defined as one that is one standard deviation within one standard deviation of their mean. So one standard deviation above or one standard deviation below become the borders, and if the response or the daily well-being score the next day lies within that, it can be considered a typical response because that will account for about 66% of the responses that an athlete will have to that specific stimulus. And this is where these values come in for the between group, and these values come in for the within group. And what we've done that here. So a typical athlete could be expected to have a daily well-being score of 38.32 to 59.88 in response to the low sleep the previous night. So again, low sleep the previous night is 49.1, more or less. And then a typical athlete could have 49.1 minus the between athlete standard deviation, so 38.32, all the way up to 49.1 plus the between athlete standard deviation, which makes it 59.88. So if you have an athlete who has a response within those two scores, they could be considered kind of like more typical, whereas those who have a score below that could be considered kind of like hyper responders to low sleep in terms of they really struggle with low sleep, and those above that could be seen as not struggling as much with low sleep. And of course, the problem with that with a random intercepts model is that those who always give high wellness aren't necessarily low responders to sleep. It could just be that their normal wellness is 80 or 90 and they've actually dropped 20% to 60 and they're still above that. And this is where the benefit of having the sleep as a covariate within the model will become clear as time goes on. Next, if we look at a player's individual response to low sleep, this can vary by 10.59 either side of their mean, and this is where the intercepts that we've looked at become really interesting. So using athlete 9's low sleep as an example, athlete 9 has a low sleep of 35.70. If we subtract athlete 9's, so I've done that for high sleep. Okay, even better, so I made a mistake here. So athlete 9's low sleep is 35.69, which means one standard deviation below is 25.1, and one standard deviation above is 46.28. So let's change that now. And you can see how there's a really big difference in the values that you can then expect from athlete 9 compared to the mean. So for athlete 9, we'd expect anything from 25 to 46, whereas between athletes, we'd expect 38 to 59. So athlete 9 could actually be a low responder from a typical response to low sleep, or could actually be deemed a low responder at the between athlete level within their typical range. And this is where the within athlete becomes really important. So that's what we can take from the interpretation of the random effects. And really, you want to work at the within athlete level as soon as you can. But the between athlete differences can provide an initial understanding of what's going on and group everything together. So if you have a new athlete, you could almost like try and see what group you think they're in as soon as before you have enough data to run them within a model themselves. And then within athletes, you could potentially use that standard deviation difference either side to see if there's something else going on with their wellness score. So if they're massively below that one standard deviation below the wellness that you'd expect, then perhaps they could be at risk of injury or illness happening in the future, although there's no research actually looking at that at the moment. Next, let's move on to the covariate model. So as we said before, the trend appears to be virtually linear between low, medium, and high sleep. So now what we could do is we could look at the model where we use the mean-centered sleep variable, the continuous random intercepts mixed model. And this is the model that starts at line 48 and finishes at line 63, if you want to run that in SAS. And it's even easier to compare everything in this one because we don't have all of the pairwise differences. And this is the benefit of using a covariate where you're looking for a rate of change almost. So you're looking at for every hour increase in sleep, what would be the expected increase in daily wellness, as opposed to we need to compare between the means of two groups, which will have different hours of sleeps and are only compared on the basis, are only included on the basis that they are less than or fall within a specific criteria, i.e. less than -1 z-score, more than +1 z-score, and in between the two. Now we know for every hour difference what we would expect to be the difference in wellness score. And we've done everything exactly the same. As you can see, I've got the pooled standard deviation, which again is the sum of these, and then square root it. You've got your standard deviations here, which are done in the same way as above, so just square root the estimate, lower and upper. And again, you can see the between athlete standard deviation has more uncertainty than the within. The only estimates we need now to do our comparisons are the 1 hour sleep, so we know what the estimate for a 1 hour sleep is with the effect sizes here. Again, divide by the pooled standard deviation. The intercept for +8 hours, athlete 9 for +8 hours, so we can compare the between and within athlete standard deviations. And then that's it. So let's have a look at the effect size first. So there was a significant but trivial relationship between sleep duration and subsequent daily well-being score. Again, significant, but the effect size is less than 0.2. So the effect is trivial. And then we have the intercept and the athlete 9, which we'll come to in a second. So the summary was that the effect of 1 hour difference in sleep duration on the following day's daily well-being was significant, but it didn't constitute a meaningful effect when Cohen's d effect sizes were used. And this almost comes to the debate about whether Cohen's d effect sizes are appropriate or not, because it's easy to state that sleep isn't related to differences in well-being, but we don't know what a meaningful change in daily well-being is. If it's a 0 to 100 scale, then a 3% difference could actually be considered meaningful because a 1% difference is findable. Whereas if it's one of the more commonly used, 20, 25 point scales that's been converted to 100, then it's probably not, because a 25 point scale means every unit is a 4% difference. Or even a 10 point scale means every unit is a 10% difference. So knowing more about what your outcome measure actually is and how big those differences actually are is helpful. But another thing we could look at is a 1 hour difference actually the right scale to use, given that sleep cycles are 90 minutes long? Should we be looking at 1.5 hours? Should we be looking at 2 hours, 3 hours? And these are all things that can make a big difference in terms of the outputs that you get here. So it's things that you have to question and be aware of what you're actually doing. What's a meaningful value of a covariate, and then what's a meaningful change of the outcome measure. We've then got the within and between standard deviation quantities here. I will do the same thing. We'll do the same thing with the interpretations we did last time. So let's say that we have a 1 hour, so if we experience 8 hours more sleep than normal, which is obviously extremely unrealistic, but it just goes with the estimates that we produced last time. We use the between athlete standard deviation, add and subtract that to the estimate, and rather than just saying that 8 hours plus for the average athlete would give us an estimate of 80.14, we can change that so that we have a range now, which is 69.4 to 90.9 as their subsequent daily well-being score for the typical athlete if they experience 8 hours more sleep than the average amount. So that takes into account 66% of the athletes would fall within that range. Within athletes, the typical response to sleep has a similar range of expected results, i.e. it's 10.4 either side as opposed to 10.74. which means that for athlete 9, if they've had 8 hours more sleep than normal, we would expect a daily wellbeing score between 57.0 and 77.8. And again, that is just this number plus this number, and then the same number minus that 10.4. And again, it gives a range of responses we expect without actually calculating every single thing that happens. So we haven't calculated any of the train load, any of the outside stress in this. We just know more or less how they'll feel in a general situation, and it could potentially give a warning sign then if they don't feel as good or as bad as that in response to the sleep that they've had. So you can see how it's a bit more individualized now in terms of using the 1 hour sleep rather than just grouping into a minus, plus, or in the middle Z score, and gives us a lot more sensitivity to what actually happens within the monitoring data. But we then took that one step further and said, well, some people will respond to sleep and some people won't respond to sleep, and it goes back to what I was saying before in terms of athlete 9 is a little bit different to the average amount in terms of athlete 9 could have a low sleep response that is within their normal range, but could actually be considered a non-typical athlete, even though at the top end of their range they could be considered a typical athlete according to the Z score, kind of like between and within athlete standard deviations. So now what we could do is, with this next model, we could say, right, well, what is the actual response to sleep? How does sleep actually affect this athlete by using the between athlete sleep standard deviation? And to do that, we need to use the continuous random sloped mix model, which ran from lines 70 to 85, so that's this model. And in this model, again, we've only included the covariance parameters and the estimates. We've selected which estimates we want to look at. And as you can see, the covariance parameters are now bigger than they were before. Before it was only 2 lines, now it's 4 lines. And this gives us the between athlete standard deviation, the between athlete standard deviation in the influence of sleep on subsequent day well-being, and the within athlete standard deviation. And again, the pooled SD this time is a sum of the 3 elements. So the elements that we are interested in whenever there is an on there are just the ones that have the same number in brackets. So 1, 1 and 2, 2. We're not interested in the 2, 1 because that is a covariance between the 2 measures. So we sum 115, 2.4 and 103, and then square root them to get our pooled standard deviation. And if we square root the individual elements of that, we get the between and within athlete standard deviations. Could then move on to the estimates. And again, we have the 1 hour sleep estimate, Intercept +8, and athlete 9 +8. Effect sizes are worked out in the same way again. So now we can say there's a significant relationship between sleep duration and subsequent daily well-being. So that's significant because, again, we have p less than 0.0001 there. And I've put, which may have been small in magnitude, because you can see that it literally, the confidence intervals are both sides of the border, and it's literally right in the center. So 0.20 is a small border, but when you can see it's 0.15 and 0.25, it's difficult to be fully confident that the effect was actually small. And we'll come on to the intercept and athlete 9 in a second. So as above, the increase in sleep duration on daily well-being score was significant, but I put only possibly meaningful given the lower confidence interval of the effect size, which is below 0.2. And so it may result in a meaningful difference in daily well-being, it may not. Caveats of above are still relevant, so looking at, should we be looking at a 1 hour sleep difference? Should we be looking at, should we know what the daily well-being difference that's meaningful actually is, etc., etc. And then the within and between athlete different SDs remained fairly similar, but there was a standard deviation for the between athlete differences in the influences of sleep on daily well-being score, and this was 1.57. So we can calculate the between and within athlete differences as above. So you can do that again yourselves if you so wish. Remember, that's 8.95 plus 10.75 and minus 10.75 for the between athlete typical daily well-being score, and then 86.36 plus 10.16 and minus 10.16 for the within athlete typical daily well-being score in response to 8 hours of extra sleep. But now what we can do is we can really work out these responders or non-responders to sleep duration by using the between athlete sleep standard deviation. And what we can do is we can add and subtract that from the 1 hour sleep estimate. And if we do that, what we find is that a typical athlete would expect a 1.44 to 4.58% increase in daily well-being. So any athlete who does not experience a 1.44% increase, so is less than that, could be considered a low responder to sleep. And this could affect the way that you look at their wellness information, if you know this, because it may well be that actually in response to an increase in sleep, their wellness doesn't shoot up in the same way that you would expect. Likewise, for those whose estimate is greater than 4.58%, you might find that you probably want to consider this when looking at their wellness data, because if they have a massive increase in sleep and don't massively increase their wellness score the following day, then potentially there's something going on there. And in case you are unsure of how to actually get each athlete's individual sleep change, all you need to do is take out the intercept terms that we used before. So this is a 1 hour difference in sleep for subject 9 or participant 9 with the confidence limits. Where did we go? One up. When the model runs, so it takes into account these adjustments now, the MC sleep _SAS random effect adjustments. And so athlete 9 is a 5.28 for every hour of sleep, a 5.28% increase in daily wellness score. And as a result, they are considered a high responder to sleep. Hopefully that all makes sense. So now that we understand how to interpret all of these mixed models, we're going to move on to start extending mixed models in the next video.